Work and energy are two of the most fundamental concepts in physics, and earlier in the course we discussed their application to translational motion. Now we will see that these concepts are equally as useful when applied to rotational motion, provided they are expressed in terms of angular variables. In Chapter 6, we defined the work done by a constant force as W equals F times S, where F is the magnitude of the force that points along the direction of the displacement. Let's rewrite this expression in terms of angular variables by considering the following situation. A constant force F is applied to a rope attached to a point P to the outer edge of a wheel with a radius r causing it to rotate. As the wheel rotates through an angle theta, point P sweeps out an arc length distance s. Since the force is applied tangentially to the edge of the wheel, it will also point along the direction of the displacement of the point P. Therefore, we can calculate the work done as W equals F times S. Since S is equal to r times theta, the work becomes F times r theta. We group the F and r together and recognize that this product is the torque applied to the wheel by the tension force F. Therefore, we write the rotational work as W sub r equals torque times theta. Here, theta must be expressed in radians, and the SI unit of work is joules. We might have expected this result for the rotational work. Since work in general is force times displacement, rotational work should be equal to rotational force, or torque, times angular displacement, or theta. From Chapter 6, we showed that the work done on an object by the net external force was equal to the change in the object's kinetic energy. Likewise, the rotational work done by the net external torque must be equal to the change in an object's rotational kinetic energy. Imagine one point mass in the wheel, say of mass m1, and located at a distance r1 from the axis of rotation. This mass will have a kinetic energy equal to 1/2 m1 v tangential squared. We write the tangential speed in terms of the angular speed. V tangential is equal to r omega. Making the substitution and regrouping the terms, we find the kinetic energy is equal to 1/2 mr squared times omega squared. The total rotational kinetic energy of the wheel would then be equal to the sum of the kinetic energies of each of the masses that comprise the wheel. We pull omega outside the summation since it has the same value for every point on the rigid object. However, we recognize that the sum of mr squared is just the moment of inertia I. Therefore, the final expression for the object's rotational kinetic energy is 1/2 I omega squared, where omega must be expressed in radians per second, and the energy will be in joules. Just like rotational work, this result should not surprise you. For translational motion, the kinetic energy is equal to 1/2 times linear mass times linear speed squared. Likewise, rotational kinetic energy is equal to 1/2 times rotational mass, or moment of inertia, times angular speed squared. Kinetic energy is one part of an object's total mechanical energy. Now we take into account both the translational and rotational kinetic energies that can result simultaneously. A wheel rolling down a hill, for example, has both translational and rotational kinetic energy, in addition to its gravitational potential energy. The rotational kinetic energy term now gets added to the overall total mechanical energy. And as before, in the absence of work done by non-conservative forces, the total mechanical energy is a constant of the motion.